All right. So we talked about this yesterday. But if you guys think about it, you guys know, I'll just use an ant, for example. You know, like ants have like, little teeny tiny like legs, like walking around. Why don't we see like giant sized ants? Like ants as big as horses with like those teeny tiny little legs. Why don't we see that? It's the same reason why little kids can hang from their arms for so much longer than adults. Like at the school across from where I live, we have some monkey bars, and my kids were having like they're timing how fast they could go across the monkey bars. I can't even do one monkey bar. I hang on my arms for like 1 second, and they want to dislocate. And it's not because I'm not as strong as my kids are. I'm much stronger than my kids by like a lot. It's because of something called a square cube law in nature. And here's the reason why. We're going to talk about animals in this case. So, the mass of an animal or a human or what have you depends on its volume. Its volume. And volume, you guys have all taken grade 9 math, volume is like a 3D concept. But the strength of an animal, so the strength kind of depends on, if we're talking about ants and why their legs are so skinny, or we're talking about elephants and why their legs are so massive. The strength of an animal, or we're talking about a hanging child, the strength depends on the thickness of your legs or your arms. It depends on their cross-sectional area, and that is a 2D thing. So the strength of an animal depends on I'll tuck this in here, the area of its muscles. So that's not like a technical term. It's like a cross-sectional area. So if you imagine slicing through like your bicep or something, it depends on the thickness, the cross-sectional area, how big they are. And area is a 2D concept. So what happens if an animal doubles in height? Let's say all of its proportions double. It's like well, we're gonna look at King Kong in a second. But an animal, all of its proportions get twice as big. If an animal doubles in height, its mass increases by a factor of not 2, because as height changes, the depth changes, the width changes, its mass will increase by a factor of 8 if an animal doubles in height and everything stays the same. However, its strength doesn't increase by a factor of 8. Its strength only increases by a factor of 4, 2 squared. So this is the idea. So as you keep growing and growing and growing, in terms of like why my kids can do the monkey bars, it's because my mass has increased by so much, but my strength hasn't caught up. It can't get caught up. So that's why it actually hurts if I just like hang by my arms. My arms get really tired really quick. I can't do it. But little kids can hang forever. And it's the same reason why little mice have these teeny tiny legs to support them. But we don't see big animals like elephants have these little teeny tiny skinny legs, because as they get bigger and their mass increases, their legs have to get even thicker to support their mass. This is called the square cube law, and it's represented by this equation right here. As we call kind of the strength factor required for an animal to kind of support its own weight. H2 over H1 is like the ratio in heights between an animal kind of growing from a height H1 to H2. And the exponent of 3 over 2 just comes from 3D volume and 2D area. I want to do an example with you guys. So you're all probably familiar with like the King Kong movies. So I don't know how tall King Kong is in the actual movies. I think its height actually varies depending on the scene he's in. But let's say that King Kong is 50 meters tall. Let's say an actual gorilla is about 2 meters tall. I don't know. Oh, this would be a perfect time to do like a 100 humans versus one gorilla thing. Missed opportunity. Um, we'll say a gorilla is 2 meters tall. I think they're a bit shorter, but let's just keep the numbers round for the sake of comparison. So King Kong is like 25 times as tall as a normal gorilla. In the movies, all of King Kong's proportions are 25 times the original, right? He looks like a normal gorilla in the movies. And if you watch him move around and fight with his like weird robotic glove or whatever, like he moves pretty good for a huge 50-meter tall gorilla. He's very agile. Would you guys agree, King Kong aficionados? He's a very agile gorilla for being 50 meters tall. But that's full of crap. Let's talk about why. Let's say normal gorillas' legs are 0.4 meters wide. In the movie, King Kong's would be about 10 meters wide. But let's look at reality. Let's look at how thick King Kong's legs would have to be to support his weight if his mass increased by a factor of 25. So let's calculate this required strength factor. King Kong's height is going from 2 meters to 50 meters. So follow along, everybody. Let's calculate this strength factor for King Kong. So the strength factor, it's the ratio of his heights, the big one divided by the small one, to the exponent 3/2. Now you guys can calculate this. You should be able to almost without a calculator. 50 divided by 2 is 25. And you guys can do 25 to the power of 3/2 using our new knowledge. We talked about this yesterday. Your calculator can do this. But as your math teacher, I would like to see you demonstrate our new rules. So let's apply them here. Can you guys rewrite that as a root? And then we'll get an approximate answer for that. So this is the over 2, which means just plain old square root of 25 to the power of 3. So 5 to the power of 3. Do you guys get 125? Yeah. Here is the significance of this number. If King Kong's height, I'm going to type this out. If King Kong's height increases by a factor of 25, King Kong's height increases by a factor of 25, his leg size, must increase by a factor of 125 in order to support his weight. I chose a really big font for that. Let me reduce that a tad. 20? That seems okay. Perfect. Now, what would that look like? We said our gorilla's legs are 0.4 meters wide. So how thick would his legs be if you were to multiply by this strength factor? What is 0.4 times 125? 0.4 times 125. If the original gorilla's legs were 0.4 meters thick, 0.4 times 125, King Kong's legs would have to be 50 meters thick. Guys, for King Kong to be able to actually just stand and not collapse underneath his own weight, his legs would have to be as thick as he was tall. So here's what King Kong would actually look like in the movie if we obeyed our square cube law. His legs would have to be this thick. They have to be I'm just like, it's a silly drawing. But no, his legs, in order for King Kong not to just have his legs completely snap underneath his own weight, and that'd be a pretty pathetic movie where King Kong jumps in the scene and immediately both of his legs fracture and he just mewling on the ground in pain. No,